Hello and welcome to lesson 5.3. Today we're going to look at the second part of electron configuration. Now if you recall, yesterday we talked about the three principles and rules that described how to fill our orbital diagrams. And if you remember, each box represents an orbital. So here I have an s orbital because there's only one box. I have another s orbital because there's one box. And I have three boxes together, which makes this my p orbital. If you recall, we can put one or two arrows in each box, depending on how many electrons we have. Now in each box, we can put at most two arrows, and if we have two arrows in one box, then one has to be up and one has to be down. So today, we're going to start out by looking at an example, and we are going to look at writing an orbital diagram for carbon. So for carbon is element number 6 right here. So what I notice because of the periodic table that I'm given is this is actually in the p level, okay, but I have to account for all the electrons that come prior to that. So when I go to hydrogen and helium make up my 1s orbital. So I'm going to write my 1s orbital because this is my first row in my s orbital, and hydrogen and helium will fill in the first two boxes. So I'll cross those off. Then my 2s orbital is second row s orbital, which are these two right here, or lithium and beryllium. So I'm going to cross those off because I'm going to fill in that 2s orbital. And then I'm going to come over here into my p orbital. So I'm still in my second row and in my p orbital, but carbon is the second element in. So I have 1, 2 elements in. So remember, when I fill in like my p, d, and f orbitals, I have to put one electron in each orbital before I can start doubling them up. So here I have my first one electron in each of the first two boxes or the first two orbitals. So now if I just go and do a quick double check, carbon has 6 electrons and I have 2, 4, 5, 6 electrons. So this is how I would represent carbon. Now if we go and we try to do something a little bit trickier, so let's look at another example here. So let's write the electron configuration of something like iron, which is element 26 here. So iron, and I'm just going to put that there are 26 electrons, and I get that, and I know it's kind of hard to see, but if you look on a periodic table, the atomic number is 26, so we have 26 electrons. So what I'm going to do is I'm going to draw, and you can draw boxes if you want. I personally am going to draw lines. So I'm going to have my 1s, then I'm going to have my 2s, and if I fill these in as I go, my 1s is going to have 2 electrons, and again, that's hydrogen and helium. My 2s is lithium and beryllium. Then I'm over here onto my second row, and in my p's, we know that we have 3 orbitals. So second row p orbital, and because I'm going to use up or go through all of these, I'm going to have 1, 2, 3, 4, 5, 6. Now I'm going to jump down to my third row. So I have my 3s level, and both sodium and magnesium are going to fill that. Then we're going to jump over here, and we have our p orbitals again, and I'm third row p block. So I have to get through all 6 of these, which tells me that I'm going to fill in these 6. Now I'm down here into my f orbital. So my my fourth row, I'm back into my s, so I have 4s, and I'm going to take potassium and calcium are both going to go in there. And now I'm down into my f block, and I'm just going to slide this up here hopefully. Okay, so now if you look here, I'm in my my d block. This in here is my D block, and my D block, if you don't remember when we talked about this a couple days ago, D has 5 orbitals. Remember, S is 1, P is 3, D is 5. Well, 5 orbitals holds 2 electrons in each orbital, which means 10 electrons. So when I go to draw this out, I'm going to draw my 5 orbitals, or 5 lines. So I've got 1, 2, 3, 4, 5. And I am now, remember in my D, we are 1 row off. So because I'm technically in my 4th row here, this is actually going to be the 3D orbital. And if you can't remember how many electrons go in an orbital, count them out. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that means I have 5 blocks because 2 electrons can go in each block. So now when I come back here, I have selenium is going to be 1, titanium is 2, vanadium is 3, chromium is 4, manganese is 5, and when I get to iron, that's 6. So now I'm going to start doubling up. So this right here would be an orbital diagram for iron. Next, we're going to look at what we call the electron configuration notation. Now, the electron configuration notation is actually very similar to the orbital diagrams, except you're not drawing the arrows in the boxes or the lines. We're going to kind of squish it all up and just do the 1s, 2s, and so on. So what this does is it describes the principal energy level and the energy sublevel that is associated with each orbital. Now we're going to have superscripts, and this did not come through properly, so we're going to ignore this for right now. You are going to have superscripts. So by superscripts, a superscript is actually this right here. It's kind of like the power. Okay, and the superscripts are going to represent the number of electrons in an orbital. So if we go and we look at the example of carbon, okay, carbon, again, is right here. So to get to carbon, I have to fill my 1s orbital up first with hydrogen and helium. So my 1s orbital is going to be full because I'm going to put 2 electrons in there. Then I have to jump down to my 2s orbital, which is right here. So I have 2s. Well, both lithium and beryllium are going to fill that. So I'm going to put a superscript of 2. Then I'm going to come over here, and I'm in my P block now. And it is my 2p block because it's in the 2nd row P block. But now notice carbon is the 2nd element in. So I'm going to put a 2 up there for the 2nd element. Now, a way that you can double check your work is if you go and you add up all your subscripts right here, it should give you the total number of electrons that you need. So here I have 2 plus 2 plus 2 gives me 6, which tells me I really have 6 electrons. So if we go ahead and let's just do another example. So I'm going to erase all this here. Okay, let's go ahead and do another example. And this time, let's do something like, let's say chlorine, which is right here. Okay, so for chlorine, I'm going to do the 1s level. Okay, so again, that takes into account my hydrogen and my helium. And I have to put 2 electrons in there. Then I have my 2s level, because 2nd row s level, and I'm going to fill that up with 2 electrons. This right here is going to be my 2p level. Well, the 2p level will hold up to 6 electrons. And again, if you forget, count them out. 1, 2, 3, 4, 5, 6. Now I'm down into my 3rd row, and I'm going to fill in my S level with sodium and magnesium, so that's going to be 2. Now I'm over here into my 3rd row in my P block, so I have 3p, and here I've got 1, 2, 3, 4, 5 is going to be my chlorine. So now I'm going to be 3p5. So again, let's just double check our work here. And if I go through and I add up all of my superscripts, I should hopefully end up with 17 electrons. So 2 plus 2 plus 6 plus 2 plus 5 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 7, or 5 equals 17, which is exactly how many electrons chlorine has. Okay, now this is the same thing with chlorine. If you would have done 1s and you did your 2 arrows, then we would have had our 2s with our 2 arrows. We would have had our 2p block like this. Then we would go into our 3s, and then we would go into our 3p, and 3p then would have 5 electrons. So it would look something like this. So if you notice, numbering everything down below actually corresponds to all this up here. So the 1s, it says it has 2, well, I have 2 electrons right here. The 2s has 2, I have 2 electrons here. All the way down to when I get to my 3p where I have 5, I've got 2, 4, 5 electrons here. So the 2 actually do go hand in hand. Now, we're going to do kind of like a shortcut here. In your homework, I will tell you when you are allowed to use the shortcut, okay, because you have to be able to do both. But we're going to use what we call noble gas notation, and this is a method that represents electron configuration of noble gases. Now, if you remember, our noble gases are the elements that are in this outside row. This is what every atom is trying to look like, configuration-wise. These elements have 8 valence electrons and are very stable. Okay, usually they're very hard to react. And they're hard to react with because they have 8 valence electrons and they don't want to give any up because they don't want to lose that stable configuration. So when you have a noble gas, like, so let's look at neon. Okay, neon means everything is full. So if I do it with, let's do noble gas and electron configuration at the same time. So I'm going to have 1s2, which means I'll have 2 arrows here. Then I'm going to have my 2s2. And then I'm going to jump over into my 2p, and I'm going to fill up all 6 of those. And again, you can double check. If I count my exponents, I have 2, 4 plus 6 is 10. Neon has 10 valence electrons. Okay, so now the noble gas notation comes into play because I know that any element that is in this column is going to be full up to that point. So if I want to go and do something like magnesium, okay, so let's look at the example of magnesium. I'm going to use noble gas notation, and noble gas notation means I'm going to put in brackets the noble gas that comes before. So magnesium is right here. The noble gas that comes before magnesium is neon. So I'll put neon in brackets. And what that tells me is that all of this is full. Then I see that magnesium is in the 3rd row and it's in the s orbital, so it's going to be a 3s2. So this is noble gas notation. Okay? So let's go ahead and look at another example. So with helium, helium is right here. I could write helium as 1s2, or because it's a noble gas, I could just go ahead and put it in brackets and we would know that everything is full. Likewise for neon, we just did neon. I could do 1s2, 2s2, 2p6, or I could just write neon in brackets like that to indicate that neon is already full. Now when I get down here to sodium, sodium is this element here, okay, in the 3rd row. So this would be 1s2, 2s2, 2p6, 3s1, or what I could do is I could say, well, neon is the last noble gas that comes before sodium, and then I'm in my 3rd row, so I'm just going to go 3s1. And just because we can, let's come down here and look at something like, we'll say strontium, which is element 38. Okay, so if I want to do the electron configuration using noble gas notation, I'm going to come to the noble gas that comes before strontium, which is right here at krypton. So I'm going to put krypton in my brackets. And then strontium is in the first, second, third, fourth, fifth row. And I'm in the S2 spot. So that would be my strontium. Now I could do something like this for, let's come over here and let's look at bromine, which is element 35. Okay, so bromine, the noble gas that comes before bromine is actually argon. Okay, so argon comes in the row before, so then bromine is going to be in the fourth row. So now I have 4s2. That takes care of potassium and calcium. Then I have to go through all my D's. So I have 3D, and my D levels will hold up to 10 electrons. So when I do my 10, that gets me all the way through zinc. Now I'm on gallium, and I have 5 electrons left to go back into the 4p level. So this right here is a lot shorter to write out than if I were to go 1s2, 2s2, 2p6, 3s2, and so on. If you're still a little questionable on this stuff, I will go over a few examples in class with you tomorrow. Now, just I wanted to show you this just in case you saw this like in your textbook or in another science class or something. We have what we call the Aufbau diagram, okay, and that's what you can see right here. And what this diagram does is this will actually tell you which sublevel comes next. So here you can see we fill the 1s, then we fill the 2s. From 2s we fill 2p, then we go to 3s. Here we go from 3p to 4s. Then from 4s we're going to go to 3d, 4p, and 5s, and so on. Now this works great when you have the chart. However, I myself like to use the periodic table like I've been showing you, because chances are especially like on a standardized test, they'll usually give you a periodic table, but they won't give you a diagram like this. So if you understand how to use the periodic table, I think you're more apt to have a periodic table handy than the diagram itself. So if you look at this real quick, you can see that we fill in our 1s's, and that's going to be the same thing as if we had the periodic table, because we know we fill in our 1s level first. Then it tells me I go to my 2s. Well, these are my 2s. So I got this checked off. Then from 2s, I go to 2p, and then to 3s. So here's my 2p, and then my 3s. Then from 3s, I go to 3p, which is right here. And from 3p, I go to 4s, which is right here. Now once I go from 4s, I'm going to come up here and go to 3d. Well, this is all my 3d here. And from 3d, I go to 4p, which is exactly what this says. And from 4p, we go to 5s. And so you can see how the periodic table and this go hand in hand. But again, my preference, okay, you can use what you want. My preference is to use the periodic table because I think it's something that you're more apt to have on hand there. And the last thing is, I wanted you to kind of start looking at a periodic table and being able to recognize, okay, where your S, P, D, and F stuff is, because you're going to have a periodic table more like this. So just know that these two columns here are going to be your S's along with helium. So these are S. Your P's are going to be like these tall blocks over here. Oops, I went a little bit far down here. Okay, so my P block is going to be everything over in here. My D block is going to be here in the middle, or the transition element region. So these are your D's, and then your F's are these two bottom rows down here. So please kind of start making that connection, and if you can use a periodic table that doesn't have that labeled, that would be even better yet on your homework, just to kind of get in the habit of being able to recognize where everything is. So on that note, I hope you have a great day, and I will see you guys in class tomorrow.